delay. Will you resume in 1 minute, or like I will wait for some more people to arrive? Can we do a quick check on the synchronization? Same way we were doing previously. Let me share my screen. Just let me know when if there is any lag. Now, so A, B, C, D, E.
No lag.
Oh, nice. My house Wi-Fi is better than the office Wi-Fi. Okay. We'll just wait for a few more people to join. Hopefully, everyone will be able to join. This very sad state of affairs, this delay. But okay.
You can just post in the group, no? I think.
Yeah, I emailed. I sent an email.
Was it?
I initially messaged that it would be better if the Chrome size is a bit bigger. Is this fine? Or should I make it like really big? This will be ridiculous. Okay. So, okay, great. We have 11 people almost. No, exactly 11 people almost. So in the meantime, like I think we'll go wait for 15 people to join, and then we'll start off again. So in the meantime, are there any questions from the previous thing that we were doing, which is basically the compilation of library, compilation and packing into a library, archiving into a library?
No.
Oh.
Yeah, what is the difference between this and shared library?
Okay, good question. So let's create a shared library first, and then we will see what is the difference. So the way you create a shared library is this object file that you were packing into this, or putting in this, archiving into this .a file. .a means .archive for Linux. For Mac OS also it is .a, I think, except for Windows. In Windows it has a different name. In Windows, .so is called DLL.
DLN.
Shared is called something else. Yeah, Windows, I am not very sure. Ravi will know. Ravi does Windows stuff. So for shared library, we'll just create a shared library first, and then we will. So by the way, are there people here? Should we start off? Like, I don't want people to miss this part just because of a silly Wi-Fi issue. Okay, I'll start that once 15 people are there. I'm just waiting for 2 more people.
Okay.
Or should I message people individually?
Your message in the email saying start.
Don't even remember who all were there.
Should I put it in the WhatsApp group?
Oh yeah, we have a WhatsApp group. Sorry, I kept it on mute, and I've been missing all the notifications there. Yeah. Can you please send that?
Yeah.
You muted that group. You were saying,
I have
chat.
muted all groups. Basically, like minimal WhatsApp notifications, because otherwise my phone was going ting 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 all the time. So many groups I've become part of. Can't leave also, otherwise people will feel offended. So think. Ravi, are you recording? Actually, why are you waiting? It's being recorded. So if we, yeah, okay. Okay, then if people are missing, then yeah, okay, they can see it from the video. By the way, everyone got the link to the last day, yesterday's videos, no? 2 sessions.
Yeah.
Fine. So we'll continue. So marking on shared library, right? So we will build. So this was building a static library. Static terminal library. And now we'll build a shared library, and we'll see what is the difference. So the thing is, you don't type it. You just put your same .o files into a shared library. How do you do it? Okay, sorry, the syntax for this. Wait, shared, and then you have minus. You can get the name of the output that you want usually. So lib slash lib thermal. So it's usually a mention to start off names of your libraries with lib. That's why if you go to, for example, any of your slash libs, you will see a lot of this lib. This .so is what we're going to create. Okay. So obj solver dot o. Okay. Now, if you want to link this library, there are multiple ways you can do it. Okay, let's try this way. Let's see what happens or what happens here. It will create a .so file and it will try to link. It says no such file or directory. And it also says that relocation something against cannot be used while making a shared object. But this is a different thing. We'll just temporarily, I'll put something. We'll talk about this later. What this symbol means. This is just a FPS means position independent code, which has some meaning. Like if you are into gaming and like PUBG stuff and so on, and if you like cheat codes, you are basically using code which doesn't use position independent code. So. Oh, sorry, file exists. This one thing I'll get rid of. So if there's already a file present, folder present, you can not make those things by using this. And this was supposed to be fine. Why is it not compiling? That's weird. Oh, okay. Sorry, my problem. If you want this to be compiled into a position independent code, but put it's just a linker. This won't do anything. Put in the compilation step. So obj solver goes here. This one is FAC, which means use position independent code. Okay, so it compiles. And if we go to run and we do an app, it says we got it. Okay, now we'll do a dissection of what this shared library is and this static library is. So a shared library essentially means that the library, in this case the libthermal.so, will always be separate from the functionality contained in libthermal.so will always be separate from the functionality contained in the executable, which is your app bin/app. Okay. A static library means that if you are linking the library, so let's quickly segregate these two. And this was the way we were doing static library, right? So let's call it static app, and this we will call shared or dynamic library app. Shared library. Okay, shared app. Here we are going to link with .so. Here we are going to link with .a, and we are going to. So this is shared library stuff, okay? And this is static library linking. Yeah. Now, the difference between the two is if we just go to compile these two and look at the bin. So there are two things in the bin now. If you do LDD basically tells you what are the dependencies of this app. If you look at shared library or bin/shared library, it will tell you I have these many dependencies. Out of which there is one which is called libthermal.so. Okay. Instead, if you go to static library, there's no libthermal.so. So basically what has happened is in the static library, if you link to the static library, all the functionality contained in the static library will be absorbed into the executable itself. So definitely the size of the executable will increase. So now if you look at, okay, well, in this case, it will be minuscule because there's hardly anything in the solver function. But if you look at the sizes of these things, about so it will be different in a few bytes maybe in this case, but sorry, it will be there in a few bytes in this case. But for a big library, you'll see that the executable with the, so basically, as you can see, the app is the same size as shared as a static in this case. So just remove the app for now. The shared and the shared library will be much smaller than the static library because the functionality of the shared library has not been absorbed into the app itself. The side effect of using a shared library is that you will always need to separately ship the .so file apart from your executable, or make sure that the customer who is running your code has a version like this. Okay, on the system. But if you include a static library in your app itself, then the customer doesn't have to install anything separately. It's already included in your executable. The other, that is the pro of using a static library. The con of using a static library, or the pro of using a shared library, is that shared libraries are called shared or dynamic libraries because, see, I have compiled the app now, right? So this is done. So let's say I do bin/shared app, it will give me 62.008. Now suppose I find out that this is a bug. Okay. I want to correct this bug and ship it to the customer, but the customer has been compiling all their codes and all their libraries and all their forward dependencies using my library. So it's a big tool chain which they have to recompile again if I update my static library code. Because static library has to be continuously recompiled. Instead, if I gave them a shared library like libthermal.so at the beginning itself, then I can just create a modified or new libthermal.so and give them just that. It will execute the final app, since it is not hard. The functionality of libthermal.so was not hard coded into app. It will just dynamically point to the new libthermal.so and use the new functionality itself. As long as the function signatures remain the same. As long as the API or the function signature remains the same, the contents of your libthermal SO you can swap between .so files. And that is why if you go to your Linux kernel or your distribution, you'll see .so 00.1, 0.10, .9. So basically, okay, let's take this for example. There's a .10 and a .9. What it means is basically that, okay, usually the versioning is, okay, it depends on the version syntax that they use, but I don't know exactly, but as an example, the function signature or the API signature between these two .so library function, like whatever functions they contain, will not be different. But the implementation of the content of the functions will be different in these two cases. One might be a bit improved than the other. One might fix a bug. One might be fixing performance and things like that. Okay, so let's do that actually. What we'll do is we will not compile our executable. We have our shared app here. Let's just change our library itself. So we'll comment on all the app compilations. So now we just create the solver.o, our library.o. We create a new static library and we create a new shared library. We're not recompiling the app again. So now, if we just go in and change our solver.cpp to suppose in the update case, we are going to be a bit nasty and just do in init case, we just do pulse plus 10 internally. So I'm not changing the function signature, I'm just changing the contents of the code. Now suppose I recompile only the library, not the executable. And now if I do /bin static, you see I'm getting the same value because new functionality has not been included in it. But if I do shared app, you'll get a different value or the new value. Okay. Because if you do LDD, it picked up the new signature. It's a dynamic, it's like a pointer. It points to the library. It doesn't include the functionality directly into the code itself. Okay. So this is the difference between shared and static. So it depends. Now it depends on the project, the client, what they want, and so on. So some people try to reduce the size of the exe file or the executable file that they're generating and shipping. That in that case you have to use .so. Some people, especially people who are using legacy code, obviously you don't expect people to be storing .so files from 1980s in your new systems or Ubuntu distributions or Linux distributions and so on. So those legacy libraries, they usually convert it to static libraries and pack it up with executable only. Or if you're using web app development, almost everything is like shared libraries because it's so dynamic. Every week things are changing, new features are coming. You can't keep recompiling everything from scratch. That's why it's always shared libraries. You can just drop in a new shared library and start working as long as the API is the same. If there's API difference, it's called API or backward incompatible. Then you have to create a major version change and then people have to recompile their shared library linking code also. There's no other way. So, okay. So this is roughly the thing. And usually you have a cleanup stuff later on. So let's uncomment these. So for the test code also, we were going to change them. So there's a test vendor, there's a test.cpp, and you can, depending on what you want to create, you can or how many lines you want to do it in, you can keep building your test codes like this. So, again, the way I'm writing all these things, it might seem redundant, and there might be a better way to do these things rather than doing all these things. That's exactly why you need CMake. CMake is like a meta language to generate these kind of scripts or make files by themselves by writing a simple meta code. So we'll just go into CMake right now, except let me quickly finish up this example so that we can compare it against. This would be, so you can either create a test library or you can directly link the code also. It's up to you. So usually it's better to make it modular and link it. So we'll create a shared library for the test cases. We'll call it the terminal tests. And we'll include all the OBJ. Yes. You can compile test.cpp also into .o file. Just do that actually. And then link all of them together into a single file. That is the library. The way to do it is, if you really want to see the sequence of things, this is how you do it. /test.o, and we'll pick up lib thermal.so. Thermal.so, right? Oh, thermal.so. And like we will need to include the actual solver functionality also. So we'll do a thermal.so as well. I think this should suffice. And if you want, you can do a minus over here. The front end in slash lists. Not sure, it might not compile, breakdown somewhere. Okay. It says headers are not found for something, test init. Because I haven't included minus I dot vendors. I will need this also. This was that. How many does it happen? Oh, it's a long compile time business. Yep. Okay. So we are going to now move to CMake. So are there any questions regarding shared libraries, static libraries, any of the steps that we did right now? Because if there are questions here, then there will be a lot of additional questions in the CMake step. So if you're sort of comfortable with this, then we can move on.
No questions from my
No
side.
question. How many people are there right now? Has everyone joined back? 14. Okay. I see. Okay. So let's quickly comment our code and so by the way, let's just verify that the tests are actually working. No tests ran. Why? That is weird. Just give me 1 minute. Sorry. Wait, one small thing is that this will fail. Okay, let it fail. Because we changed that plus 10 thing, so it will be wrong results. But that shouldn't be the case here. Just let me quickly figure out what to debug. Yesterday, someone was catching the bugs left and right. Is that person here today? Yeah, this should work, hopefully. No idea why the test is behaving like that. Okay. It is possible that catch doesn't support position independent codes. So what we'll do is we'll remove position independent stuff from here and recompile them.
What position independent code means?
So basically, okay, position independent code means this. Usually, if you really want to know this, no, then it's a very nice topic on how your program is loaded onto uh, the stack space, and then the data is allocated in heap and so on. So basically, okay, roughly speaking, like this, it's like this. When you don't use when you compile without position independent code, your this option, essentially your which function resides at which memory address. In the end, when the compiler is writing the compiling the code and producing the output, either in terms of assembly or object file or the executable, final executable or the library, it is essentially writing down or like you can imagine almost like a text file, no? With that move, add, and all those things, line by line by line. And the location of those lines are basically corresponding to memory addresses where these lines are being stored or where this file is being stored. Okay. Roughly. These are very vague terms I'm talking about. There's a more exact definition to all these terms, but just give you an idea of what is going on. So these are like the memory addresses where each instruction is stored for the entirety of the program. All the lines in the program are correspondingly stored at some lines. Without using position independent code, essentially every time you load the code, when you execute the code, the sequence of these lines or the memory addresses where it is loaded will remain the same. Now the thing is, if that is the case, then depending on your architecture or your OS, like where it is allocating stuff, or even in terms of security. For example, if you're always loading in the same area, no, and if someone with really malevolent intentions knows that you're using on like position dependent code or something like that, well, that's not the exact opposite, but okay. Then they will be able to basically try to do an exploit where you keep trying to read off bits in a particular location and figure out what is going on. Okay. So instead, if you start jumbling your positions, okay, then it is nicer. But so mostly it is based on security itself. Like nowadays, the other reasons which used to be there in the earlier architectures for doing position independent code or not and so on are gone. Mostly nowadays it's security based. So basically, if you do FPIC, you will be safer.
Okay.
But we don't care. It's just that the shared library and the static library business also requires position independent code for. Sorry, the shared library requires position independent code for C++ for a certain purpose. You just have to use that in that sense. Okay. So yeah, so if you just don't use position independent code for this thing, your catch tests, because catch somehow uses something internally, you have to see where it conflicts with it. Then it should work out nicely. So you can remove this also. Okay, for now. Need this also, right? So it's failing because we made that small change intentionally. So we'll go back and change that to not plus 10. Even by in state. We'll just clean up our comments a bit here because it's looking. So we'll just get status, get at. I won't complain because this is my own creation. Quickly, check out. maybe not. What? 8 comments. Oh my god. Wait, what is the graph here? Oh, we did not commit anything there. Huh? Okay, fine. We'll get rid of this. We will just go to that branch. What was it? Fixing. We'll git push, and it will tell us that there's no stream, so we will push it upstream. Now we'll see here quickly. Visualize what is the issue here. And now we'll merge. Nice way. We're merging to main. Proof merge. Let me just clean up all these branches once, huh? Because they're creating a lot of havoc. This is merged, so I'm clean here. This is 7 comments behind. Okay. Let's bring it to a clean state. This is fine. Branches. Okay. And here also, just to be safe, I'll delete all the unnecessary things because I keep making these mistakes. Well, everyone will make these mistakes. Because no one was finding out yesterday. Very common error. It's doubly difficult if you have shot yourself in the foot by restricting direct pushes to master itself. Clean? Yeah, you're clean. Okay, now we have a clean slate. Okay, so we'll now go into CMake. So first we'll again create an issue. Let's do it nicely now. We verified the temperature with analytical, no? So we forgot to branch out the issue from here. We'll just close the issue, saying solved. So build using CMake. That is the new topic. We will be merging this back, so we'll create a merge request. And now we'll get pull, synchronize, get checkout, 6 step. Okay. So now what we'll essentially do is this compile.sh that we have written, it looks a bit dirty. We'll see how to programmatically, like we'll consider all these objects that we created, these .o files, these .cpp files, these executables and so on. Think of them like, suppose you were supposed to programmatically generate all these files in an object-oriented manner, like using classes. So essentially you'll have a class type called object class. Then you'll have a class type called executable class. Then you'll have a class type called library class. And libthermal.a, libthermal.so will be instances of your library class. Like lib is the class type, or library is the class type, say. And then libthermal.so would be an object of that type, and so on. Similarly, if object is a class or obj is a class, then solver.o will be an object of that class or instance of that class. Okay? Similarly, for executable, you'll have tests or app and so on. So CMake is basically that. It lets you treat all the intermediate files as objects in a program, and then you can add properties to it. Like you have member functions in C++ classes, you can have member functions defining the properties of an object. What are the properties of an object? For example, if you are going to compile using std minus C++, minus std C++11, there's a property of the compiled object that it has that C++ functionality inside it. Then if you are going to use -03 as a compile flag, or as an optimization flag. That it means that the compiled object will have -03 level optimizations inside it, and so on. So essentially, if we are going to write a pseudocode, so if CMake was supposed to be a CPP file kind of thing, then you would have had class library something like objects here. So here the property would be suppose, let me call it a prop or bool, has position independent code. Like this would be a property. Then if your object file was a class, then you would have has std c something like that. And then in your main function, your actual script, you'll be creating objects like this. So, oh, by the way, you'll have a source file also, so source file or .cpp file, that is what it's called. And here you'll have, suppose, std string file name. That's obviously that property is there with every class file name actually. So suppose here you'll create first source file solver cpp is you'll load this source file, right? src/solver dot, and then you'll create a library object file out of it. So object we'll call it suppose solver obj is equal to compile this solver cpp with some extra flags like minus stdc plus 11 sorry, or -03 and so on. So this is how you would programmatically do it, and then you will take a library, create a library by doing something like terminal equals link or archive if you're creating a static library, where you'll be putting the solver obj file. Or you can put the other list of other files also if you have things like that. So CMake is like this, except syntax is not exactly this, it's a bit different. So let's write a CMake file. The CMake file or the CMake script that you write is called CMake lists.txt. Usually you'll have something like add executable, or okay, let's define a setup. So the simplest thing is this: add executable. You'll create an executable in this. Suppose we are going to call it app. Then you'll have src app.cpp. You could have written something like this is the name of the executable, like name, and these are the files or srcs. But CMake doesn't like to use commas and all those things. It's like this. Okay. And if you had another file, you would have added it like this, like solver.cpp. Oh. So, and if you want to include header directories, then it becomes property of this app that is being compiled. So you would say that target include directories, target meaning the target object, which is in this case app, target app, and you can put in the headers. So headers would be include directories basically, so include. So this is it. I think this will compile. So let's try that out once. Are these two lines clear? Or very simple, right? These are
app, no? Or
so basically, okay, when you create the executable called app, by default it will get the name itself as app, and app is also a symbolic link for the object called the executable. Okay, so this acts both as the name of the app. So basically, you will end up creating a app in your there will be a app object in your folder when you compile this, and also for referring to this CMake instance of a executable class type, it's also called app. So essentially, it would have been exe if exe was a class defined in CMake is actually written in something, not C, something else. But anyway, so if executable was a class defined by CMake with all different types of properties, here essentially what this line is doing, this add executable line is doing is executable type app equals, and then you put a constructor. Okay. Where you pass in the list of files. which you're going to use to build it. Okay. So this is what CMake is doing essentially in that step. It's a very roundabout way of doing it because these are like global functions. If you really want an object-oriented way of building stuff, check out Meson. Meson is a Python-based build system, very similar to CMake, much cuter, but CMake is very old and very powerful because it has been around for a long time, and most of the industry, for all practical purposes, every C and C++ code nowadays is built by CMake. Okay. So I think this will compile, or you'll be able to build it.
Somadip, that solver.cpp, that executable also there in app will be embedded in app.
Yeah, so the way it has been defined right now, solver.cpp will, contents of that will be completely included inside app. If you want to now separate it out into library, I'll come to that. How to first create a library and then include the library in the app, or link the library to the app. So right now it will just be a single app, no library business right now. Okay. So this won't. Okay, this will. You need 2 lines of metadata, but let's first see how to compile, like, or create CMake. So CMake will not compile directly actually. Okay, CMake will just throw out a make file. Make file. I didn't go into the make file because I'm pretty sure you can find out there are enough make file tutorials, or you have come across some make file in your life here and there. This is a nice way, a nice example page where you can see how make files look. So like we created that compile.sh, make files look very similar, except you can do some linking also. Like if you define intermediate auto files, you can use those things directly in the next line to link it and so on. So this is how a make file looks. It's quite similar to our compile.sh. So that's why I didn't go into it much. And since we don't use make files that much, we use CMake, we'll directly go into CMake. And CMake is more programmatic. So make file is like shell script, CMake is like Python. It's not a straightforward analogy, but in terms of programming, that's how it looks. This looks almost like shell script. CMake will look a bit like Python slowly if you start getting the hang of the objects there. Okay. So how you come? So what CMake does is essentially CMake will create make files or compile.sh for your program the way you have defined it. CMake itself will not do the compilation. So the first step is CMake will spit out the make file, and then you use the make file to compile. It's a makefile generator, CMake. Okay. So the way you create this makefiles is you say CMake minus s, where is the source code and the starting of your, or the first CMake script that is here itself, the CMake list.txt. Or if you were outside this folder, suppose this thermal has your main code, right? And the CMake list.txt script. So you would say CMake minus s thermal. And then you have to give a build folder where it will do a lot of intermediate building files and all those things. First, making the CMake make files themselves. Okay, so minus build, and that's it. So this is how it works. Then it's supposed to throw out some make files in the build folder, and you can go into the build folder and do make, and it will compile the whole thing. Now, what it is complaining about is I haven't given a project name. So usually in CMake, you have to give a project name and a version name. So, and what version of CMake you have to use? So CMake, I think it's called minimum version required or something like this, is it? Let's quickly check. Let's keep CMake minimum required. Why is there no simple syntax? Yeah, okay, CMake minimum. So this one here, you just give the version number. So usually people nowadays use modern CMake, which is version 3.15 and above. So you can just minimum required is 3.15. Older CMake was a lot like, C in that sense that it is not, C is not a good example of an object-oriented programming language. Okay. Like you can create structs, but that's it. You can't put member functions inside that and so on. In modern CMake, you do proper, like you treat each intermediate file as an object itself and attach properties, attach functions, and so on. So that's why modern CMake, which is actually coming up from CMake version 3.5 and above, uses these new syntax like target, include directories, and so on. But before that, you would have to do something like include directories and then list out directories, and then then this would be included globally and so on. So Older CMake used to use older CMake used to use a lot of global variables and so on, which was not very good for scoped applications. So one is CMake minimum required version, and the other thing is project. You have to give a name to your project. In this case, I'll call it thermal, my thermal library or something. Hash won't work. Underscore. That's it. So now it should create the CMake files without upgrading. So let me quickly clean up the build directory. Now we'll do CMake -s thermal -p build. Sorry. Version has to be there. It's called version 3.5. Otherwise, what is minimum? I don't know. Yeah, so what does it say? Target. Oh, sorry. This is one more small thing. Later on, when you're building libraries, you'll see that. Okay, let's give an example right here. What is missing? To do tree, you'll see that there are two types of HPP files that you have included in this code. One is directly an include, which is your library solver.hpp, which will be used, as I was saying yesterday, as almost like a reference documentation for people using your library. It exposes the API, like what all functions you have created in your library. It's like a one-line summary of those things, the API of that. There is also another HPP file here, which is like an internal HPP file, which you're using just to create the tests. The user does not need to know whether you're testing your code or not. How you're testing your code using Catch or using Google Test and so on. The user doesn't care as long as it's tested and stable. So there are internal header files and public header files. Okay, internal means private, like you don't really need to expose it outside and so on. So CMake, modern CMake actually makes a nice distinction between these two, because there can be cases that suppose Catch requires C++17 internally to compile some functionalities. But your code actually requires only C++11. You don't need to ask the user to use a C++17 compliant compiler to use your library and so on. So then you can say that, okay, for Catch, compiling the test part, just use C++17 and make it private so that it doesn't get exposed or carried over to the user side. And for the user side, you separately compile C++11 wala header for the solver.hpp, and it is a public thing, so user will be able to see this header file. So that way you can segregate different types of compilations also. Like suppose you are going to compile a compute bound code separately with certain compiler flags and memory bound code separately with certain compiler flags. And the problem is if you combine the two compiler flags and try to compile the entire codes as a single unit, it would have given you a very horrible performance. So this is actually in real life we have seen. Like if you try to add together the optimization flags for both memory bandwidth, optimized performance and compute optimized performance, you'll actually start reducing the performance of both cases. Okay. So, so what we'll do is in the CMake script, we will just say that this include that we're directly including, which has solver.hpp is a public. And if you wanted to separately include we have not really compiled the test, but if it was, test was also included, you would call this private test/vendor/ this thing. Right now we don't need this, so we'll just leave this out. Again, we'll go back. Yes, my source is this, or the root CMake script is in this folder, and I'm building into this. Done. So if you now go into the build folder, you can see what all has been built. There's a lot of intermediate done files. There's all basically CMake trying to figure out what kind of a make file should be created. In the end, you'll see that CMake has effectively created this make file, and you just need to make on this file. So if you look at this, you'll see this is the kind of very generalized abstracted out make file it has created specifically for your case. So you should see some solver.cpp mentioned somewhere here. So as you can see, solver.o is being created first from this thing, solver.cpp.o and so on. So it is basically CMake has its own algorithm to generate very generalized make files. This looks like this. If you were as a human going to write your make file, it would have just been two simple lines. But okay, let's not look at this. Let's CMake do its own dirty business. And you usually compile using makefile by doing make with the makefile. Okay, so you do make here. That's it. So now you have a compiled app. here. And if you run the app, 62. This is how you compile. So as you can see now, effectively your compile.sh, which was that big previously. Okay, we have explored a lot of functionality here. So let's assume that we were building using this part only, the app part. This thing is now condensed into a nicer looking object-oriented thing like this. Those two are just metadata, so you can forget it. Like it happens only once in a project, so don't count those lines as being bloated. So this is it. Now we want to compile a library and link it separately, explicitly. So what you do is, instead of add executable, you do add library. As I said, there's a library class, there's executable class, and all those. So this we are calling thermal. CMake will automatically add the lib part to in front of it and .so or .a to after it. So you can tell whether you want a static or a shared library and so on. So here we'll say static, okay, for this case. And then you'll say what are the files required. So solver.cet is the library. And then you need to say that we also need a target directory, which is this. And here the link should be for the library itself. So thermal is the link or the object which is containing all the properties of this library. Then for add executable, you don't need this. It's just the app. You need to link the library. So what you'll say is target link library. It gives you the option to link multiple libraries. So here you'll say app link library. There's only one library, so what you'll do is you'll link thermal. I'm just typing up. I think there might be a syntax error, but we'll see. And for this, do you need the include? Yes, you'll need it because you need a interface to tell the compiler what that library contains. Yeah. So this will basically create a static lib solver.a or solver.a. We'll have to see the name of the file, and it will use it to compile separately the app executable. So let's do that. Then let's go outside. Let's do CMake -s thermal -p build. Okay, it says build. If you so one more thing about make files and CMake files is that if you make changes in one file, it won't recompile the other files for you because it will look at the timestamps and all those access modify changes and figure out that, okay, if there has been no change since the last time you compiled it, why increase the compile time by random, again, recompiling the same thing which hasn't changed again, and so on. Okay, so that's why you're seeing it's happening very fast. But if you remove the build state, previous build state altogether, then it will have to start recompiling from scratch. So now you can see, again, it will start compiling from scratch. So first we'll identify what all compilers it is going to use. By default, I use GCC 9.3. So it's identifying that and so on. And this has maybe a compatibility. This is not important. So if you go into build, again, if you look at tree, there is quite a few more files now. But you will see that there is a where is the app? Okay, there's no app because there's only a make file because we haven't done make yet. So there's a make file, and if you want to run the make file to actually do the compilation, you just run make. And here the compilation happens. So as you can see, it says I'm linking C++ static library, okay, which is libthermal.a. We gave the name thermal. It appended a lib and prepended a lib and appended a .a to it. Very nice. And it also created the executable app by linking to this thermal. So if you look here, there's a libthermal.a sitting here and the app sitting here. Okay, very nice. And now, if you want to change the name of your files and so on, you can also add other properties like set target properties. You'll call it thermal. Suppose I want to call my library revolutionary thermal or something like that, like we were trying to call it yesterday. Then you can say output name. Name should be, instead of thermal, you use thermal as the object itself, but when you're writing it, give the file name as ref thermal. Okay. And here you won't say ref thermal because it's a file name, or call it ref thermal.so or something, or libref thermal.so. I don't know what you call it. Here I'm still going to use thermal because thermal is the name of the object itself. It's a variable essentially, and this is the file name. There's a difference between the two. Okay. So let's compile this again. For cleanliness, we will delete the build folder, and we can -b for the build. Sorry. Just give me 1 minute. I think there's one small syntax error I'm doing. Properties. Yeah, you have to give the target name and then call properties and then give the property key and value. So small things. You always Google properties. These are the property lists. Then the property. So usually you can break it up also. So this is the name. This is the property, and then what are the property name key value pairs? Key is output name. Value is the file name. And so you can structure like this also if you want nice indentation. So we'll just build it again. Yeah, done. So now if you see, go into thermal or go into build, you will see that you have a make file. You go in to a make. It says it is doing lib-thermal.so.a. Okay. The reason is that we did not specify whether it should be. Let's go quickly. Thermal. So now we can see that it's anyway going to prepend lib, whether we like it or not. So let's check the lib out of it. And we did a SO, even though we called it a static. That's why it said, okay, I'll treat it just as a file name and then append.a because you told me static and so on. Okay, so we should like leave it with this. That'll be fine. Let's not go out this time. We create a new library, build folder here itself. So CMake -s dot is this folder and build. Okay. I can go into the build here and do a make. So now it's fine. There's a lib-thermal.a. Okay. So this is how you basically generate things using CMake. Except there's a small syntax or a good etiquette while doing CMake is, since you are using CMake, best not think that it generates make files and then you have to use make. You use your CMake to generate the make file, that is okay, that's the first step. Then you say CMake --build, whatever is there in your build folder. Effectively, we'll call make on the build inside the build folder, but you do like this. Okay. So that way you don't have to keep going back and forth between make and CMake, because those are conceptually two different things. Make compiles, CMake creates make files. It's like you're going between the mother and the parent and the child. Let's stick with the parent only. Okay. So this is how you build it, and then once you're done, you can choose how to package it and so on. So are there any questions regarding CMake? This is basics of CMake. If you want to go in really deep and see some good practices of CMake, you can go to this repo called, again, in systems, using CMake. There are quite a few options that are given about compiling with different compilers and MPI, OpenMP, and so on. And there are a good list of references about good practices, a bit more introduction to how to look at CMake and things like that, how it is object-oriented and so on. Okay. So any questions regarding CMake? Is it too fast, too slow? Again, do you want me to explain a particular portion which might have been a bit confusing?
Actually, you explained nicely through that,
Okay.
Giving reference to object-oriented stuff. So it was good.
Yeah. Okay. So everyone agrees with that?
What?
No, everyone agrees with that? Everyone else?
Okay.
With what Bharati said?
Yeah.
Okay, fine. Okay. So can we make it a habit? Then basically, see, if we stop using compile.sh or make files, you can use make files. I have nothing against make files. CMake itself creates make files in the end. Just the thing is that make files are a bit of shell scripting. Like it's like shell scripting, right? Like if you now look at the CMake list.txt, you will see that it is more like object-oriented, like a Python or a C++ program, and make files are like shell bash scripts. They do the job, it's fine. It's just about a bit of elegance and process management and things like that. So if everyone now makes a promise to use CMake, then we can officially tell our parent company that we are a CMake approved, like we are a CMake compliant company. Can we put that in the documentation? So the reason I'm asking this is because if we put in documentation, next audit people will start asking, the audit team will start asking, okay, show me which all libraries, how they're using CMake. And every library has to use CMake.
I think most of us are using CMake, no? I don't know other groups, but in our group, we are using CMake almost.
Okay, fine, fine. So this is the basics of CMake. So let me know if you want to go into, want me to explain something else again, one of these topics again. The way we package using CMake, actually, you know what? The best place to learn CMake is from CMake tutorial itself. So there's, if you go to CMake's page, by the way, this is the same company which makes CMake, makes Parallel also. So it's a very good company, Hitware. So if you go to their documentation, there will be a tutorial. Just go line by line through this tutorial. You will know CMake like in and out. There is nothing more to CMake, or there is, but practically for all practical purposes, there's nothing more to CMake than what is there in this tutorial. The 12-step tutorial, if you are stuck with something, they actually have given you code which you can go through while going through this tutorial. So first of all, I just put in the link of the tutorial here in the reference. Anyone wants to see it right away. And if you want the link to the code, you just, CMake is an open source software, so you can go to CMake GitLab repo, and you'll find the code there. CMake also uses GitLab, so you can actually see how much metadata they have in there. So this is their actual code, and this is the metadata. So metadata triumphs actual code nowadays. You can go to help and guide tutorial, and here you'll see for each step they have just given all the like intermediate steps of the makefile scripts also step by step. They're basically trying to make a pi calculator, square root function calculator. So the C code is very simple, you don't have to bother about the C code. How to create a makefile for creating libraries using that C code and package it into .sh. So if you have installed Mathematica or I don't know what Mathematica or any other so-called exe file on Linux, what you usually install on Windows, if you install the corresponding thing on Linux, you'll see that it comes with .sh file. Like if you do just .mathematica.sh, it will start self-extracting and installing things and so on. This is how they do it. Okay. Like if you just create a package using CMake, you'll be able to package your codes like professional developers and distribute them across other companies and get revenue and be the employee of the month. Okay. So yeah, you can look into CMake lists that are shown here. So that finishes CMake for me. If there is no more questions about CMake per se, then we can go to the next topic. I'll just copy paste the tutorial rights link also here. Okay. CIC pipelines. Acha, by the way, now Sunil was asking, when are you people breaking for lunch? Because I screwed up the timing here because of the Wi-Fi issue. So what do you want to do?
Now,
Now you want to break for lunch. Okay. And will there be enough time to have lunch properly, relaxed way, and then come back at, or do you want to push that to 2:30 or 3?
I think we'll come back at 2.
Okay.
I'm
Yeah, exactly. No, this others can also say, no, at least comment in the chat if it's okay or not. Just write 2 or 3 when you would prefer to come back.
2:30 is fine, man.
2:30. Okay.
Yeah.
Okay, fine. Average. Okay.
I mean, yeah, you guys take a call. I mean, I'm okay with 2 also.
Okay, is there anyone who is going to have proper, full feast and not be able to come back at 2? Now to everyone will say that. Everyone will say, no, I eat only fruits and nuts. Okay. Fine, then we'll come back at 2. Okay. I won't take much of your time. Okay, fine. We'll get back at 2. Okay, then bye.
Yeah.
Sure.